example, what I would like to do is consider a vector, or a trajectory rather, that is parameterized from going from A to B. In other words, I'm going to have some trajectory r of t that goes from A to B as t increases, the parameter value. So what I'm interested in is if I can figure out how to measure how far I go along that arc, or arc length, or the length of that curve. The definition of that length is the integral from A to B of the roots of the sums of the derivatives. So if I define r of t as f, g, and h of t, then I would form this sum underneath the radical. And you would recognize that this really is just the length of that vector r prime of t, and so that I end up with that definition for my length of my arc, dt. All right, so I'm just going to keep going along. Remember that r prime of t is really just a tangent vector along t along r rather, as t increases. So what I'd like to do is just take a real quick example of being able to figure out, well, now I know the circle of a radius r, and I start and go all the way around, is that the circumference is 2 pi r. So let's try to do that in our new parameterized version of math, so that I'm going to parameterize that circle as r cosine t and r sine t. If I do that and allow the value of the parameter to go from 0 to 2 pi, I'll trace out a complete circle. And so that I can also compute the derivative of r prime here and find that that is minus a sine t, r sine t and r cosine t. So that when I form this length integral, the length is the integral from 0 to 2 pi all the way around the values of the parameter, and then form the square root squared plus r cosine t squared dt. Okay? And when I do that, the r squared, sine squared plus cosine squared is going to be 1. The r squared is going to factor out as an r, 0 to 2 pi, and I'll just have my square root value of sine squared t and cosine squared t. Okay, so that value underneath the radical here is 1, and so that I end up with my length being r integral 0 to 2 pi of dt, which is r 2 pi, right? Which is the length that I was looking for and expecting for the circumference of a circle. So let's look at a slightly more complicated problem that has a three-dimensional vector, right? So I have the vector e to the 2t, 2e to the 2t plus 5, and 2e to the 2t minus 20. Okay? And I'm going to let the value of the parameter t go from 0 to the natural log of 2. And what I want to know is, what is the arc length as this vector goes from its initial value to its end value? So I need to compute several derivatives, right? Here's the x component derivative, and that's pretty simple, 2e to the 2t. And then I'm going to square that, because that's what the value is that I'll use in the sum at the end here. And so I end up with 4e to the 4t. Okay, so that's going to be one of the values that I'll use. And then I also look at the y component and its derivative, right? And then that is 4e to the 2t, and then I square that, 4e to the 2t. There's no derivative. Yeah, that's okay. And then here, and then I'll just put it all in together, and that's 16e to the 4t. And now I have one more component to do, and that's the z component. Minus 20 derivative is 4e to the 2t. And I'll just have another copy of this one, because that'll be the y component. So let me label these. That was the x component, that's the y component, and that's the z component. Okay. So now I can put this all together. The length is the integral. Now those are the limits of values of the parameter. And then I can create then this radical that has 4e to the 4t plus 16e to the 4t, and then again for the z component the same value, e to the 4t, and I'm integrating that with respect to t. So then I end up with, well, here's 4 plus 16 is 20, plus 16 is 36. I'm taking the square root of it, so I end up with my 0 natural log of 2, 6e to the 2t dt. Okay, so what that, let me just do this on the side here, that if I take the square root of e to the 4t, that equals the square root of e to the 2t squared, which then, by the rules of exponents is e to the 2t. Okay? And that's where I got this value. So then we do that integral and find out that that is 3e to the 2t evaluated from the 0 to the natural log of 2, and we find out that that value is 9. Okay? So the length of this curve, r, is given by that value there, 9. So that's an introduction to the length of curves.